All right, we are going to be talking about the graphs of trig functions. So in particular, the graphs of sine and cosine today here in lesson 3.1. So graphs of sine and cosine, again, these are the graphs we're going to be looking at. We're going to be looking at the graph of y equals the sine of x and y equals the cosine of x. And also some transformations of these things where we stretch them or shift them or do other changes to them. In general, these graphs, these two graphs are called sinusoidal curves. So kind of sine steals the show with the name, but yeah, that's just kind of the name. Another name that we use here are waves sometimes, waves, because the graphs are kind of reminiscent of waves, and they also apply to some physics problems and properties involving light and sound and electromagnetic waves. All right, let's go ahead and move forward. So here is a graph of sine, along with a table of at least the first part of it. And what you're going to notice here is our x values, our angles. And these are just some angles that we can find along the unit circle, right? So 0, pi over 6, which is the same thing as 30 degrees, and then 45 degrees, pi over 4, 60 degrees, 90 degrees, and so on here, right? So the x values are our angles. Those are the inputs of our trig function. And the y values here, these are actually just the sine value on our unit circle at those particular spots. So the sine value at 0 is 0. The sine value at pi over 6 is a half. The sine value at pi over 4 is root 2 over 2, and so on. So yeah, these are just the values we find on the unit circle. And it creates this nice graph right here. Obviously, we don't have any points sort of in between them, but you could imagine, right, if we had a value for, whatever, 15 degrees or 10 degrees or whatever that radian equivalent measure would be, we'd have something in here as well. This is a continuous function. These functions can take any angle that we want in there. And so this is our first, what we're going to call period or cycle. So this is one period or one cycle of the sine graph. And again, the inputs of this function were the angles. We specifically looked at unit circle angles, but they could be other ones as well. And the outputs were the y coordinates on that unit circle, and creates this super cool curve, which we call a sinusoidal curve. And because of the nature of the unit circle and the sine function, this function is periodic or cyclical. It is going to keep repeating this pattern right here, this one pattern forever and ever. So it will continue and do it again and then do it again, because of what's happening, right? We're going around and around this, well, sorry, other direction. We're going around and around in a counterclockwise fashion around the unit circle. So we keep getting these same patterns on a set cycle. Anyway, we'll talk way more about that in a little bit. Here's the cosine graph, pretty similar to what we're talking about. It's shifted a little bit. We're looking at it, whatever, but this is also one cycle of it. And again, we have our table up at the top where we have our x values are the angles. These, again, are unit circle angles. And the y values, this is a little bit strange to think about and process, but the y values are the cosine values in our unit circle. Remember that cosine values are actually the x coordinates of the unit circle, but they are the y values for this function because they are the outputs. So that's a little weird thing to kind of wrap your head around. But it creates this nice curve that looks a lot like the sine curve, especially when we repeat it, right? Once we start repeating multiple cycles of this, it's almost indistinguishable from the sine curve. The only way that we can sort of tell a difference is what a single cycle looks like. The single cycle part looks different than the single cycle of the sine curve. Anyway, moving forward, here are some cool animations that we can look at. So I'm going to open this up and just kind of show visually how the sine curve and cosine curve are getting created on this Desmos animation. So I'm going to go ahead and open that up. Takes a second here. I probably should have had this open before starting, but that's all right. So I am going to open up my slider and pause it. Okay, so let's look at the sine curve. We're going to be animating the sine curve. This circle that we have here is a unit circle. So we're going to be, this point's going to be rotating around the unit circle, and it's going to be, for sine, it's going to be capturing that y coordinate because that's the output, right? So let's go ahead and play this. And as it goes, it's going to be creating this graph. So here we go. It's going, it's going, it's going down. And then I'm going to try to pause it at one cycle right here. Okay, so I pause it a little bit after a cycle, but we went around the unit circle one time, and we captured all of the y coordinates, and it created at a particular angle, right? Notice how our x-axis is the angles. We captured all the y coordinates, those different angles, and it creates this curve. And what happens when we go around again? Well, nothing's really going to change. We're going farther out on the x-axis here because we're getting a bigger and bigger angle representing more than a one rotation, but we're still just capturing the same y coordinates. So this graph should repeat as we continue out forward from there. And let me just let it play. I'll try to stop it near 2 cycles, and I'll just pause it now. Okay, so now we've gone around the unit circle basically twice, almost twice here, and you can see we've created one cycle and another cycle, or period, of this sine curve. I'm going to turn the sine curve off and try to reset this slider, and we'll do the same thing, kind of examining the cosine. Now the cosine, again, is a little stranger because remember, the cosine, we're capturing the x coordinate of the unit circle, and we're turning that into the output of our function, the y coordinate of our function. So let's play this again. All right, so hold on, just to start things off, we started at a different place. We start at 1 because cosine here on our unit circle, the x coordinate is 1. So we start at 1, and we're going down, back up, and I'll stop it at 1 full cycle right about here. Okay, so that's 1 full cycle, pretty good stop. We start at 1, and as we go this way, our x coordinates are getting smaller, so this graph is decreasing until here we've at our lowest x coordinate, -1, and then it starts getting bigger again up until the maximum all the way around the circle. And that's it. We're capturing the x coordinates, turning them into y coordinates for this function. So x coordinates on the unit circle are becoming y coordinates here. That's a strange thing. It was a little easier to process, I think, with the sine curve where we were turning the y coordinates into y coordinates, but it's the same idea going here, and I'll play it for one more cycle and just show it's repeating itself again. And I'll try to go ahead and stop that again at the end. Okay, so 2 cycles. So 1 cycle here, stopping at 2 pi, which is a full rotation, and then another full cycle stopping at 4 pi for a second rotation. All right, let's go ahead and try to go back to full screen. All right, so why do we care about this stuff? Why do we create sinusoidal curves? What do they do? Turns out, especially in physics, they are pretty useful. Light and sound can be modeled using these sinusoidal waves. So light waves actually form something that looks and behaves very similar to a sinusoidal curve. Same thing with sound. The way the air compresses and expands, it creates these again, something that can be modeled using a sinusoidal curve because it has this sort of nature of oscillation where it's compressing and expanding and compressing and expanding. And light is doing the same thing. It's a little more technical with light, but the idea of creating these sinusoidal waves that have different wavelengths to represent their energy, and visible spectrum, non-visible spectrum, all that depends on the length of these waves that are happening. All right. Let's actually look at a musical representation of sinusoidal curves. So let's go here. I found this. I thought this was kind of neat. Website's not great, but when we play sound, so this one is modeled. So this C note, right? Oh no, this A note is kind of our bass, and it creates this sinusoidal curve. With a frequency, if you don't know this, but this is 220 hertz. That is a frequency. That's how fast it's oscillating, basically. And so this is the lowest note we have. And if you compare that to higher notes, the frequency, it starts oscillating at a slightly faster rate. And we compare that again to so here's a lower A down here. Here's a high A. Look at how the frequency, how quickly it's oscillating, changes. This took one cycle here to go to 1. This is 2 cycles. And we went from a lower A to a higher A. Music is pretty cool, uses sinusoidal curves to represent the sounds. This is obviously very, very simplified. I'm talking about it very basically. All right, let's go to move forward. And here is another kind of website that you can explore on your own about sine curves and sound. I'm not going to get into it during this video, but it is pretty neat and it breaks it down, really basic stuff. But if you haven't taken physics or you've only taken chem phys, I might recommend taking a look at this and seeing if it is cool to you or not. All right. So let's look at, I'm calling this the anatomy of a sine curve. So what does the sine curve look like? What are the important points? What are the features of it? And we're going to examine it. So first feature is something that I'm going to call the midline. Another word I may use for this is called the equilibrium. This is the line in which the curve is oscillating around. It's going up away from it, down back below it. And this is the exact middle. It's kind of the average of our maximum and minimum. Then we have the amplitude. That's how high our curves are going. The amplitude can change, and we'll need to be keeping track of that. Notice this is this equation, y equals sine of x, has an amplitude of 1. It goes up 1, down 1. Those are our maximum and minimum values that are on the unit circle. Here I have a couple periods outlined. So this is one period or one cycle of our sine curve. And then here's another period or another cycle of our sine curve. It goes from 0 to 2 pi. That is a full rotation around the unit circle. This graph continues forever in both directions, right? Because we can put in positive angles of any kind we want. Many, many rotations could be represented, or we could put in negative. So it goes both directions forever. In general, what we're going to try to do is graph one single period, usually the period that's right around the origin of our graph, the center of our graph. That's usually the one we're going to want to graph, unless it involves solving a problem that needs us to be somewhere else. Let's go ahead and look at the same information with our cosine curve. Sorry there. For a cosine curve, we still have our midline. It's still, in this case, it's along the x-axis. That's the center of our oscillation, the average of our maximum and our minimum values. We still have a single period here. Notice it's a little different than the period of what sine looks like. Sine starts down here. Here, let me just sketch in sine really quick as a comparison. Sine would look something like this. These would be 5 points I could use to sketch sine. I'm going to try to do this neatly. This doesn't look great, but that's okay. So that's one period of sine. Looks a little different than cosine. Cosine here, we start at our maximum. We go to the midline, down to our minimum, back up to the midline, and then up to the maximum. Whereas sine, it's a little different. Start at midline, up to maximum, minimum, midline. A little bit different. Let me clear this. But it keeps repeating the same period or same cycle, keeps repeating over and over and over forever in both directions. All right, so when we are creating graphs ourselves, what I'm going to be doing is this 5 friends or 5 points method, where I need to know 5 points to graph one period or one cycle of our sine curve. So you can see them here. I've kind of color-coded them to match the boxes. I'm going to start, when I start graphing sine, I'm going to be graphing the beginning. Where does it start of our cycle? Usually that's here, but our graph can shift left and right, so we got to be careful. It could start at a different place, but typically by default, it's at the origin. I'm going to graph where my period ends, where my cycle ends. That's simple enough, right? Right here. Usually it ends at 2 pi, but again, if we shift it or change the length of our waves, or our cycles, that could be different. And the middle. So these are the 3 points that I begin with. So the middle, what's exactly in between the starting point and the ending point. I could average those 2 coordinates together. I can find it a lot of different ways, and we will. Those are the first 3 points that I start with. And then from there, I have to find what I call these quarter points. So 1/4 of our cycle the basic sine curve at 1/4 of the cycle, which is here by default at pi over 2. Remember, pi over 2 is 90 degrees. That's 1/4 of the way around our unit circle. The default sine curve is at its maximum. So at 1, or whatever the amplitude would happen to be. And then at the 3/4 point, right, 1/4, 2/4 or half, 3/4. So this is 1/4. This is my 3/4. 3/4 of the way around the unit circle, or 3/4 of the way through our period or through our cycle. We get the minimum point. That's down here. And at -1, the default being -1, obviously that can change as well depending on our amplitude. Or if we shift our graph up or down, again, these points would have to shift up or down accordingly. But these are the 5 points we always want to find when we're graphing a single period or a single cycle of our sine curve. I'll reference these a lot. This is a good place to go back to and make sure you kind of understand where all these points are coming from. We're going to take a look at cosine as well here. So here are our 5 friends for cosine. They are slightly different. I'm still going to be starting with these 3 points here, the first, third, and the 5th point, 1, 3, 5. And you can see them here, 1, 5, 3. For cosine, these are our minimums or maximums, right? So cosine at the beginning of its cycle, which again is usually at 0 here, at 0. But if we shifted, that could change. And our ending point is usually at 2 pi, but if we change the period, or if we shift it left or right, that will change as well. That's also at our maximum. The 5th point is at our maximum. And in the middle, at the very center of our cycle, is the minimum value. Okay, and then from there, we have our 1/4 point, which is on the midline, and our 3/4 point, which is also on the midline. I plot those next. Sometimes it may be somewhat challenging to find what this number is, especially when we shift our graph left and right. We have to kind of figure out where this lies on our actual scaling of the x-axis, which is one of the more challenging things that we have to do is creating this scale. This is kind of the standard scale, and if our graph works with the standard scale, this is what we'll use. If not, then we have to kind of come up with something on our own. But anyway, those are the next 2 points we graph, and then we can sketch a nice cosine curve through those. Again, I'll be using this and referencing this method for graphing cosine as well. So you'll want to make sure to know where to find this and kind of understand what's going on here. All right, so a few things to keep in mind while we're going to be creating these graphs. 1 period is good enough. We're mostly just going to graph a single period. They keep repeating forever. The only exception to this would be if we are trying to solve a problem that involves a function that is a sine curve and trying to solve that graphically, and we need to answer a question that is maybe out multiple periods. We may want to graph all of those periods, but that's a kind of a small detail. Most of the time, if we're just creating a graph, we just want 1 period. If we want more, we may use a calculator or Desmos or something to graph as well. Second thing is make sure you scale your x and y axes appropriately. This can be kind of easy or kind of hard. It just depends. If we can use our standard scaling, which is something like this, we go from 0 to 2 pi. Pi in the middle. These would just be our quadrantal angles on the unit circle. If we can use this for the x-axis, great. Super easy. Not much to even really think about. And same with the y-axis. If our y-axis is just 1 to -1, again, super easy. We don't have to do much thinking about it. This is kind of the standard, but there are many things we can change about the graph that will affect the scaling, and we got to be careful about that. Okay, the third thing to keep in mind here is that we really only need to graph the maximums, minimums, and midlines. These are our 5 friends, right? This is what I was talking about on those last 2 slides. These are the 5 friends. We can sketch our curve through those to be sort of as accurate as we need it to be. We don't need any other points, just these to create a pretty accurate graph. So let's examine y equals sine of x. Again, this is a really basic graph, and we're going to create this one pretty simply here. So this is our standard one. It has a period of 2 pi, or a cycle of 2 pi. It has an amplitude of 1, meaning it's going to go up 1 and down 1 from our midline value. Yeah, that's really all we need to know here. So I'm going to scale my x-axis appropriately. We're going to go from 0 to 2 pi. That's our standard one circle around our unit circle. In the middle of that is obviously pi. That's halfway between 0 and 2 pi, or half a rotation. In here, a quarter is pi over 2. Again, this is all standard. And 3/4 is 3 pi over 2. So that is our 4 sections here along the x-axis that we'll need to graph those points. And then on the y-axis, we just need to have an amplitude of 1. So we need to go up 1, and we need to go down 1. And since there's no numbers here, I can just kind of scale it however big I want that to be. All right, we are graphing sine. So we're thinking about the 5 friends. So we start with the first point, which starts at the beginning of our cycle at 0. We do the 5th point, which is at the end of our cycle. And then we do the 3rd point, which is in the middle of our cycle. Pretty easy there. 1st, 5th, 3rd. We have these 3 midline values. That's how sine gets graphed. Then at the 1/4 point, which is our 2nd point on here, sine curve should be at its maximum, which is 1 in this case, amplitude of 1. We're going up 1 unit from the x-axis, or from the midline. And then here at the 3/4 point, we're going to go down 1 to a minimum value. That's the 4th point of our 5 friends. So now we have our 1, 2, 3, 4, 5 friends, and we can sketch this curve in here. Let's see how well I can do. This should be more curved than I'm really making it, but trying my best. Here we go. So this is one cycle of our standard, again, very standard sine curve, with no transformations done to it at all. But I wanted to talk about it in this most basic form. I'm going to clear what I have here. Okay, let's go ahead and do the same thing for cosine. I'm going to go a little faster with some of the things. So cosine is going to have the same scaling. We're going to go out to 2 pi, pi. Obviously that's 0, pi over 2, and 3 pi over 2. Again, same amplitude and period for this. So period of 2 pi, or 1 cycle, is going to be along 2 pi on the x-axis, and our amplitude is also 1. So no difference here. Again, this is a very stock standard curve. 1 is our maximum value, -1 is our minimum value. So once we have the scaling done, that is appropriate for our function, which it is in this case, very standard, very default. We need to make the 5 friends. So I'm going to do that in, let's just say, green. So cosine, again, I start with the first point. Cosine starts at its maximum value, right here up at 1. Because when we think about the unit circle, right, here's our unit circle, the coordinates of this are 1, 0. And cosine is 1, is the x-coordinate, so it is 1. Starts at 1. And then we graph the last point. The 5th point of our 5 friends here, cosine will end at its maximum again, because when we go all the way around the circle here, we end up back at our maximum value, 1. And then in the middle, when we get halfway around our circle, so halfway over here, we are at the lowest cosine value, which is -1. So halfway is at pi. That is our 3rd point of our 5 friends. It is at its minimum value. So again, with cosine, I start with the 1st and the 5th and the 3rd points of our 5 friends. So it's weird that I order them that way. I'm kind of ordering them left to right with the numbers. And then the other points, these 1/4 and 3/4 points, these are our midline values. These are when cosine is 0. So at pi over 2, we have 0, 1. And at 3 pi over 2, we have 0, -1. So 0 being the x-coordinate, putting our graph at its midline. Then once we have our 1, 2, 3, 4, 5 friends graphed, we can sketch this curve out. And this is again, our standard default cosine curve. Nothing special about it, no transformations. We can obviously make this a lot more challenging by doing transformations. All right, this is going to be the end of part 1. In the next part, we're going to be looking at some transformations that can happen to this graph. I'll just kind of preview it right here. So there are 5 things that we can do. I don't know why I wrote 4. There are 5 things. So there's an amplitude that we can change, so how high and low it goes. Reflection, we can flip these graphs across the x-axis. We can change the period, so it's kind of stretching it or compressing it horizontally. So instead of going from 0 to 2 pi, we can shorten that or lengthen it. This is also called wavelength. So these are the first 3 we're going to be looking through together. Then there is a vertical shift, which shifts where that midline is, kind of where we're oscillating around, and then the horizontal shift. This one's called a phase shift. I'm just going to say this one is kind of the hardest one. We're going to be examining how these things are reflected in both the graph and the equation. So that'll be what we do in part 2, and I'll see you guys there. Bye.